test. All right. What did you learn? So somebody who looked at A, what did you decide about the chips from A? Continuous? It looks pretty continuous. Yeah, pretty smooth. What did you think about the two different sides of the chip? Do you see differences in them?
Yes.
Yes. Good. Let's explain those differences.
Sneeze so quickly. Parents' questions. How was your day? Yes.
I have, yes, I have done that. It's okay. I can extract words out of teenagers. The things that you have to do, you just drive. You drive places with them, and it's funny. They start talking. All right. What did you decide about the? What did you decide about the chips of A? What did you notice about the two different sides?
One side shiny and one side's dull.
One side shiny, one side's dull. That's because shiny side rubbed against the face of the tool. The other side is just the old face. Interestingly, this is true after a lot of years. I made these a long time ago, and they're continued to be shiny and dull. Now, often aluminum will oxidize over time, and so shiny goes away. However, these will continue to be shiny, and I believe it's because it has the same oxidation level on it, but because the part is flatter, you're looking normal to the oxidation layer, whereas on the part that's rough, you're looking at it sort of edge on, so it appears thicker on those parts. That's my idea, and I'm sticking to it. Okay, heavy cut or light cut?
Light cut.
It is a very light cut. This was a light cut with the Party Groovy tool on the old manual lathes that we had. All right, what about B? What did you think about B?
I never looked at B.
Anybody have B? No? Okay, B is little, oh, they're all right here. They're very tall, very small, very curly chips. So they're all continuous, and they looped around and hit and broke off quickly. All right, C. Tell me about C. Sorry? Serrated? Yes. Ugly chips in C. Right? There is all kinds of bad things going on in those chips. They need changes to happen. They are potentially too deep a cut. They are generating too much heat. They are not operating in a happy zone. If we saw chips like that in anything but high-speed machining, we would be concerned. How about D?
Serrated.
Serrated. Yeah, it's somewhere between serrated and continuous. They're not the most serrated. I guess they do have some pretty sharp, gnarly edges on them, don't they? Okay. Heavy cut, light cut.
Heavy cut.
Compared to A, it is a heavy cut. In the world of chips on lathes, it's probably not that heavy a cut. We take big cuts on lathes. Okay, interesting. Chips. You should always look at the chips. You should pick up the chips and study them. Partially because people laugh at you, you know, when you're standing there looking at not very much of anything, and it's just funny. But you should make yourself into a chip nerd. It's cool. Some really ugly chips. I'll hand this one around. This is bad serrated. On its way towards discontinuous, except that it is continuous. Not a good way to cut things. All right, I want to talk a bit about what is happening in lab today, just so we would have the background. We are going to make little pyramids. Pyramids. On this pyramid, there are different parameters that have been used on each step of the pyramid. So we're going to look at those, and we're going to just try to understand what's going on with them, try to see what things look like. So when this program runs, you should get used to this, partially because next week, I think, not sure, but I think next week we'll do the programming for our fidget spinners, and then also in 332 we'll be looking at this same thing. So this is a setup. This means, or a job means, it is a set of machining that we do at a time before we refixture it to do the next setup. These are contours where we're cutting along the edge. So in a contour, I've selected one edge as we're going to cut this shape, and then we're going to cut along the edge. And then you'll notice I put in things called the manual NC input for a stop. So it's just going to stop the program. That's an M0. We talked about the M commands, and M2 and M3 were turn the spindle clockwise and counterclockwise, but M0, moo, is just stop, and it waits for you to hit the cycle start button to work again. So it gives you time to write things down. That's what's going to happen in lab. So when we look at these, they all happen at 10,000 RPM as of this morning. They all happen at different speeds as of last night, but now they happen at 10,000 RPM. They, on the first side, so there are 5 different cuts here. On the first side, they're going to go 100 thousandths radial depth of cut. So when we are cutting something, I have a really sweet end mill. End mill looks like that. And I am cutting into a piece of material. I will draw the piece of material behind it. Okay, now I have an axial depth of cut, so that is how far I am into the material axially. And then if I looked at the top of this, I would have a radial depth of cut. So 2 different ways that I can adjust the load that I'm putting on the tool. So axial depth of cut, radial depth of cut. So we are going to do 100 thousandths radial depth of cut on one side of the block, and then the other side is 50 thousandths radial depth of cut. We are going to keep the same spindle speed. So spindle speed is it is
12
in V over pi d, right? No, 12V, right? You're right, 12. 12V over pi d, thanks. All right, so if we were to look at what is our cutting speed here, we have pi times d times n divided by 12. And so for our cut, that's pi times a ½ inch. We're going to be using a ½ inch diameter end mill. Our speed is 10,000 RPM, and we are dividing by 12. So what is that? That's 5,000 times pi is like 15,000, divided by 12 is on the order of 1,500, something like that. So we're on the order of a cutting speed of 1,500 surface feet per minute. All right. Then our feed rate. How fast are we taking our tool and moving it through the material? And so we're going to start at 100 inches a minute and then go to 150 inches a minute. Then we're going to go to 200 inches a minute. And then we're going to do 2 that are back at the beginning parameters, but we're going to do them with a finish pass. So a finish pass means we're going to do a shallow depth, radial depth of cut, and we're going to do them more slowly when we get there. Now, something we need to understand for this is climb and conventional. So when we are cutting, there are 2 ways that the tool can interact with the material. So one of those ways, One of those ways is I have a tool with its cutting edges. This is and it is spinning this way. And if it is cutting through the material like this, there's the material, and it's cutting through the material like this. So it comes into the cut. You can see that coming into the cut, because by the time the next tooth comes around, it will have moved forward a certain amount, assuming that the material is staying still. So when the next tooth comes into cut, it will begin by rubbing along this surface, and then it will continue moving forward, and the chip will look like that. And it will take this chip and it throws it kind of out to the side and kind of forward. It depends. I mean, this is kind of a really big radial depth of cut. So the chip's going to come out and it's kind of going to go forward in front of where we're going. This is called conventional. And so conventional starts by rubbing against the surface, and then the chip gets thicker and thicker and thicker until it throws the chip. We can also do climb cutting. So I will, on this side, do climb cutting. So same tool, same rotation, same motion, but now I have positioned the tool on the other side of the stock, or if I were down here, I'd just have to be going the other direction. So when this cutting edge comes forward, it is going to hit this, and it is going to start taking a very thick chip that's slowly going to get thinner and thinner and thinner. And when it finishes, it is going to throw that chip out behind the tool. All right, this is called climb cutting. And so the last two things that we're going to do here, these two finish passes, one of them is going to be climb cutting and one of them is going to be conventional. Now, the idea is that we would, on most ductile materials, we would prefer to do climb cutting as long as we have a machine tool that has enough power and has enough stiffness to be able to do it. So we'll see if that's true. My first test this morning was not true. We'll see. Anyway, but we'll look at that and see if that is preferred. We are going to be testing it by surface finish. Have you done surface finish measurements? Did you do any of those with Mark? Okay. So in a surface finish measurement, that little stick-on thing isn't handy when it's a long way away. All right, what we do, I have a block of material here. We'll say that I just cut this surface and I want to know how rough it is. So what I do is I have a device that has a little stick out here, and then on the bottom of it, it has a diamond point. And as I drag that along the surface, so I'll drag that along the surface, and it's going to bump up and down. And what I do is back here, I have a little up and down gauge. Let's see, there's the international symbol for gauge. Yeah, I just made it up. So I mean, it's not very international. Has anybody here been to another country? There we go. It's good enough. All right, so we're going to measure the amount of up and down as we move it along, and we're going to measure that surface. And what we will end up with is a little plot that looks like this. Cut this with a circular tool. Why does it look like that? Yeah, because I'm taking scoops. So this is the scoop hits, and then it's moving forward before the next scoop hits. If I go really, really fast, if I turn this really, turn the RPM really fast and move slowly, then these little scoops overlap more and more and more, and this little point between them gets smaller. So when we measure this, there are lots of measurements that the thing will report. One of them is RZ, that is the peak to valley height. We don't like using that one, partially because the numbers look worse. Another one that we can use is called RA. And RA is the roughness average. And so you take all of your data and you do a root mean square on it, and it sort of cuts out the super high peaks and the super low valleys. And this is a functional understanding of a surface. So if I'm going to put two surfaces together and I want to know how rough they are for rubbing against each other, this is actually a better thing, because these little peaks are going to get rubbed off very quickly, and so they will go away. And so this is a functional, like a bearing load kind of number. And this is measured in a distance. For this, the distance is microinches. That's what we're going to be measuring in today. You can also measure in micrometers RA. Okay? Seem good? So in lab, we will be writing that kind of stuff down. You'll need to have some ability for calculations. They're not hard calculations, so a phone is fine. You should probably have, you should always have calipers, just because you can do, one thing that you can do with the calipers, you can also do it with a pin, is you can make surface finish measurements like this too. Because it amplifies the amount of motion on the surface, and you can feel it in the pen. There's another way to do surface finish measurements, and it's called the scratch and sniff test. And so you have a little board that has different surface finishes on it, and you take your fingernail and you rub this surface, and then you rub the board till you find the one that matches. And then you rub this surface and you find the one that matches over there. It's actually surprisingly good. One caution for lab though. All these edges are super sharp. So when we are working on these in lab, remember, you don't check a surface for sharpness by going along it, we check across it. All of these are going to be sharp, and there's no way to deburr them, and in fact we don't want to, because if you use a fingernail on that edge, you can actually get an amplification of the surface finish that's on that feature. And so it's actually pretty useful, but we just need to be careful with that in lab today. So that is lab. That's what we're going to do today, Thursday. Make chips, clean machines of chips, protect chips. It's good fun. Lots of chips. I'm clean out of salsa here. No salsa at home. Okay. You in lab.